It may sound like something from an episode of Doctor Who. Later today, though, a team of British and American scientists are expected to announce that it's finally detected ripples in the fabric of space itself.
Now, we're talking about gravitational waves, and they were first proposed as an idea 100 years ago by Albert Einstein. And what they could do is allow us to see what happened in the moments after the Big Bang. Well, let's talk to Deepali Lodhia, who's an astrophysicist, I always struggle with that word, from the At-Bristol Science Centre. And I tell you what, I'm going to struggle with it even more. Just the idea of gravitational waves. What do they look like? Well, obviously we can't see, but how should we imagine them, and what do they tell us?
So they're really quite hard to visualise, but the main thing to remember is that they're quite different to gravity as we know it. Gravitational waves are caused by very massive objects in space, asymmetric objects accelerating, so basically things like maybe two very big black holes orbiting each other. And what happens is, if you think about space and time being just one two-dimensional fabric sheet, let's say, and you've got a really big star on there, or two black holes orbiting each other, what ends up happening is that it loses gravitational radiation, and we see there's this ripples on this 2D fabric. So it's a bit like if you throw a stone into a pond, you see the ripples coming out. That's how the gravitational waves come out.
So just a second ago, we saw a kind of tubey thing.
That's right.
Okay. Tell us about the tubey thing.
That's its technical name.
So when a gravitational wave travels through space, so it's going along one direction, travels at the speed of light, and then it stretches and squeezes space all around it. And
so what do you do with that? Do you work backwards then? Is that the whole idea, that you work backwards to the point of, say, when this pebble dropped into the sea, into the water and caused the ripple effect? So how do you do that without becoming too technical?
So the gravitational wave detectors that we have on Earth, they are looking for these gravitational waves. We're trying to make the first detection because they've never been directly detected before. They've been proved mathematically by Einstein, but we're looking for the first direct detection. Once we're able to do that, it will open up a whole new window in astronomy.
How will you know when you've seen it?
So the detectors that we have, they are based in an L-shaped formation. So they have two arms. And because they stretch and squeeze space, alternately, what we're hoping to see when a gravitational wave hits the Earth is that one of those laser arms, each one is 4 kilometers long, one will stretch and the other one will squeeze. The problem is that these waves are extremely weak. So
is this them that we're seeing?
That's right, yeah. So these are the two Advanced LIGO detectors we have in Washington and Louisiana.
So they're two big rods that react to gravitational waves?
They do, yeah. So we're looking at the laser beams, we're looking at the light coming back again, and we're hoping to see a change in the length of these laser beams.
Can I ask just one other thing, really? Why does it matter?
Okay, so at the moment, we observe the universe using visible light, microwaves, radio waves, the electromagnetic spectrum. The problem is that when these photons travel through space, they can lose information. But with gravitational waves, they retain all that information. So we'll finally be able to see what's going on inside a black hole, or understand what happened at the time of the Big Bang. So it's really exciting.
Right, we're going to have another try at explaining it. Not that we didn't that time. We had to go. I'm sure people have questions about it for you. You're going to come back a bit later.
Yes, I will, yeah.
So we'll talk more. Thank you very much.
Thank you very much, Deepali. Thank you.